Hello everyone. Today we'll be talking about digital modulations. Specifically, we'll be covering binary ASK, which is amplitude shift keying, PSK, which is phase shift keying, and FSK, which is frequency shift keying. All these modulations occur through the carrier signal. For fair comparison, we will be trying to use the same average power for each different modulation. Noise can be caused through interference during transmission, or it would be added through the low-pass filter during demodulations.
Binary amplitude shift keying, or BASK for short. In ASK, the message is proportional to the amplitude of the carrier signal. So here you see that the message times the carrier signal goes through a low-pass filter, which gives us just the message and the noise at the receiver end. As previously mentioned, to result in a fair comparison, we should select constellation points that result in an average power of 1/2, so that we can compare them fairly. For ASK, this means that we will be selecting constellation points of 0 and square root 2. As you can see by this calculation here, the average power with these selected constellation points does result in 1/2. Taking a threshold value directly in between the constellation points will always result in the lowest possible bit error rate. As you can see in the bottom curve, shifting it to the right will always add an additional probability of a bit being read as wrong.
For phase shift keying, the message is proportional to the phase. We apply the message to the phase portion of the carrier signal. This will adjust it depending on if it's a 0 or a 1 to a different phase. We choose to shift it by pi because it'll shift it by the greatest distance, which will correspond directly to our binary implementation of 1 or -1. From ASK, since our average power was 1/2, we had to use the constellation points 1 and -1 in order to have the same average power. We choose our threshold from the midpoint between our constellation points 1 and -1, in this case 0, same thing as ASK.
Binary frequency shift keying, or BFSK, transmits the message using a carrier frequency. Binary FSK actually uses two different frequencies. In our case, we've labeled them F0 and F1, corresponding to a 0 or a 1. The message is sent through the carrier frequency, and when it gets to the receiver end, it's processed through two low-pass filters, one corresponding to the F0 frequency and the other corresponding to the F1 frequency. Once it's been filtered, we then take the larger value and take that as the corresponding value. As an example, if we're transmitting a 0, the low-pass filter associated with the F0 frequency will generate a 1, whereas the low-pass filter corresponding to the F1 frequency will generate a 0. We then compare the two values because of noise added from the low-pass filter and transmission, and take whichever value is higher to be the value that we receive. So if, for example, our noise made our signal for the F0 low-pass filter closer to 0, and the low-pass filter for F1 generated noise that was closer to a 1, we'd misread the bit and think it was a 1 instead of a 0. To ensure a fair comparison, we've ensured to use the same power, 1/2, for FSK. In this case, the amplitude is just equal to 1.
What we have here is the demo.m file. What that does is it takes some original message and will show what it looks like being transmitted as a cosine wave through ASK, PSK, and FSK. We can also add noise to the signal using a Gaussian distribution with a mean of 0 and a sigma squared value of 1, and show what that does to the received signal on the other end. Because FSK uses two bandpass filters, we also have a second set of noise here for the other bandpass filter. It has the same mean and same sigma squared value as before. Here we generate the different values for our cosine waves for ASK, for 1 in PSK, and for 0 in PSK, and for 1 in FSK, and a 0 in FSK. What we also have here is the demodulation for the signal in FSK for a 1 and for a 0. As mentioned earlier, FSK uses a comparison to decide whether it's a 1 or a 0. So in this case, noise and the amplitude of the signal correspond to a 1 here, and noise 2 and the amplitude of the signal corresponds to a 0 here. We also have demodulation down here for ASK and PSK, which just simply compared to some threshold value. Down here, we then graph the signals and also graph the received message on the other end. Running it will give you something like this, with random noise values and your original message on the top left-hand side. Below the original message, we have the representation ASK, where we can see the change in amplitude from a constant to 0. PSK, we can see the shift of 180 degrees, or flipping the amplitude by -1. And below that, we have the FSK representation, where we can see the two different frequencies used to represent a 1 and a 0. On the right-hand side, we can see the different representations of what we get on the other end due to the noise. So because the noise is a relatively large negative value for the first bit, both ASK and PSK, along with FSK, believe that this value is a 0 when it should be a 1. Other than that, ASK and PSK were able to get the rest of the message without any problems. However, there is a little bump with FSK due to the large negative value of the noise that corresponds to a 0, being almost -2 compared to the about approximately 0 value for the original noise. As mentioned earlier, FSK compares the noises and the amplitude to generate the value. Since the noise corresponding to a 0 is so low, it believes that the second bit is a 1. So here we have the final.m file. What this does is it generates a number of random bits. In this case, we've selected 10,000 of them, and will also give us a range for our sigma squared value. In this case, 1/4 all the way up to 16. And that's used for generating our noise, which is a Gaussian distribution. We then convert the ASK and PSK signals from the message by increasing the amplitude of the ASK signal, and by changing the PSK signal to be on either side of the 0, so basically flipping the amplitude. And we also calculate the threshold values for ASK and PSK. Here, we calculate the bit error rates for each of the sigma squared values we have for each of our digital modulation techniques. So we generate the noise on each pass, and then simply add noise to the PSK and ASK signals. We also generate a second set of noise for FSK, as it has a second bandpass filter. Here we calculate whether the bit is correct or incorrect. In this case, for ASK and PSK, we just check versus a threshold value. For FSK, we do a comparison. Our second set of noise is actually centered at our second amplitude. So what we can do with that is simply do a comparison to ever see if the incorrect value is generated. We show how this is done down here, and we can just simply simplify it to the statement that we have. After that, we calculate our theoretical values for the bit error rates, and then convert the number of wrong bits to an actual bit error rate. Then here we plot the actual thing, and it gives us a plot that looks something like this. We can clearly see here that PSK has the lowest bit error rate, giving us the best bit error rate to power ratio. ASK and FSK have basically the same simulated bit error rates and identical theoretical bit error rates.
Lastly, here we have image.m, which is pretty similar to final.m, except that instead of taking a signal, we instead take an image here. What we do then is that we convert the image into just its binary, and then we are able to run it through our modulation simulator. From there, we have our output. Depending on which one you choose, it can show ASK, PSK, or FSK. Looking at the output here, it's easiest to see the differences between ASK, FSK, and PSK with a low variance. As you can see, there is very little noise with PSK, but ASK and FSK have a noticeable amount. As we increase our sigma value from 1/2 to 1 to 2 and to 4, we introduce more and more noise. However, it's still slightly noticeable that PSK produces less noise compared to the other two, and looks closest to the original.
So in conclusion, we have that ASK is when we're shifting amplitudes, making it pretty simple to implement. PSK has the lowest BER to power ratio, and it is when we are shifting the phase. The FSK is much more complex, and it's going to result as the same BER as ASK. That is why nowadays we hardly ever use FSK. If we ever need to use digital modulations, we'll either use ASK or PSK.